Hello, this is a video I think you probably need to watch fairly close to the beginning. Probably the first one that we assign on fractions. It's just an introduction to fraction concepts, some of the things, really it's about assumptions that are going to guide our explorations and guide our teaching and learning of fractions. So there's going to be 5 big assumptions we'll talk about just to get you on the right track so you can start thinking about what concepts you need to know and how you need to use those maybe as you're teaching. There will be a couple places in this video where you'll be asked to pause and do some things, so you do need to have some scratch paper or something to write with, probably some copy paper or construction paper that you can do some paper folding on. So make sure you've got some materials available before you continue the rest of the video. So again, this is about assumptions that are going to guide our explorations. So the first assumption I really want to make make the point about is that fraction concepts and operations are very difficult. If you ask kids what they struggle with most in elementary school, most often they'll say it was fractions. I don't like fractions, and now I don't like math because I didn't like fractions. And so I want to demonstrate just a little bit of that issue. Try to show you this one at a time on the document camera. So the first slide, this is from Peanuts. Has the school bus come yet? And I don't remember who that is. Is that Linus? Mm-hmm. Says if you hadn't, you think I'd still be standing here. So obviously he's in a bad mood, right? So the next thing is, say, who's the other? Is that Lucy? I don't know. Don't know who the girl is. Anyway, she says, well, I was just trying to make conversation. And he says, well, stop trying. And her conclusion is, well, you must be having trouble with fractions too, huh? Kind of a sad situation that fractions gets blamed for this bad attitude that people have and not liking school. And here is the sequel to that. So there they are standing at the bus stop again. And she says, how can we ride a bus to school? Why don't they just haul us there in a truck and then dump us in the back with the rest of the trash? Isn't that sad? Somebody would think that, but I guarantee you have some kids who think that about their schooling. And the punchline is, still having trouble with fractions, huh? So fractions can cause a really bad attitude about schooling and learning altogether. I mean, that sounds kind of sad. The point I would try to make, though, is that there is it's somewhat funny, but there's some truth involved in it. Some humor typically is that way, that there's always a little element of truth. And it would be really sad, but I don't think it has to be that way. So we're going to look at fractions from a different perspective and see if we can maybe fix some of that negative feeling that comes from dealing with fractions. So here's my first thought about this, is why are fractions difficult? Well, maybe because they're usually taught and understood procedurally. If you remember having fractions in school, you probably just did a bunch of worksheets where you practiced, getting common denominators and adding and subtracting and multiplying and dividing fractions, remembering, there's some of those rules you got to do that sometimes I multiply straight across, sometimes I invert. Now which one it is I invert, I can't remember, it's the first or second one, all that kind of stuff. And so it's just, that's what most people know about fractions, is how to fill out worksheets on computations, very procedural. And nobody really understood even what a fraction meant when they were doing that kind of thing. So we're doing it procedurally rather than conceptually. And I don't know if we'd even call that teaching and understanding at all if it's procedural. And later on you'll get a chance, or maybe about this time you've already read the Skimp article. If you've done that article, that'll make the same kind of point, comparing relational and instrumental learning. Many people have been taught fractions from an instrumental perspective, and they don't really understand what they're doing, and they don't like it, and they're not very good at it, and it just kind of carries over into not liking math in general either, because none of it ever makes sense. So I'd make the argument that real understanding and the potential for that comfort and confidence that the kids may get, or actually maybe even you as you're learning fractions yourself, might be good motivation for exploring fractions at a very conceptual level to begin with. It might lead to some confidence and understanding. And so I think that we ought to explore making sense of fractions. Let's see if we can make sense of fractions that is probably quite a bit different than what you were exposed to when you were taught fractions when you were in school. So again, the first assumption I want to make here is that fractions are difficult. What that also means, I don't have a bullet for this though, but what that also means is that you cannot expect that kids are going to understand fractions and develop some comfort level without a significant amount of time and a lot of effort to build those fraction concepts up. If you just kind of hit a little bit of it and move on, I would say that you probably wasted your time, and it's going to just generate more frustration than it will anything else. So it takes a lot of time. And that's why in this class we're going to probably take a lot of time to develop fraction concepts. We don't expect it just to happen overnight, by magic. Okay, second big assumption. This is huge, that we must pay explicit attention to what the whole is. What does 1 look like? What does the unit look like? So all those terms, none of the fraction work is going to make any sense unless I know what 1 whole unit is. It affects all the modeling and everything else, and here's the first question that kind of demonstrates that. So if you need to stop the video and think about this for a little bit, just write down what you think is bigger, a half or a third. Write it down, or make sure you've thought about it in your brain so that you have an answer to that. Which is bigger, a half or a third? Kind of question you might be asking elementary school to answer. But the real problem is, what if we're talking about half of a mouse and a third of an elephant? Then which is bigger? We say, oh, that was tricky. You use different kind of things. But this making the whole explicit is something that kids really need. You may, as an adult, have dealt with it often enough that you know kind of intuitively that if somebody asks you to compare a half and a third, that you know that we must be talking about the same kind of pizza, or I can't really answer it. But you need to make that explicit very early on with kids so that they know that none of this will make sense unless every single time I have a fraction context, I need to know, what does 1 look like? What's the whole look like? Or I'm not going to be able to do it. If they're not the same wholes, I can't even answer a question about it. So one thing that you can do in a classroom to help kids with this is to look at 2 different size rectangles and answer that same question about which is bigger, a half or a third. So in your classroom, you could have one student fold a half and another student fold a half, or have one student fold a third and another student fold a third with a different kind of unit. And notice that it makes it very difficult. So I'll show you just a couple of examples here. If this were the whole, actually I can probably hold it up here, and I'm going to put. This is something you may have to do when you're dealing with kids. I've already folded it in half, but I'm actually going to draw a line down there so it's really clear where that fold is. Because sometimes, even with kids holding up in class, you can't see the fold very well. But now you can see the line. We would all argue that's a half based on our intuition and things that we've done before. But suppose this were the whole. Again, I'm going to put a line down there so it's really clear where that fold is. That's also a half, isn't it? But does that mean this half is the same as this half here? Well, we are pretty sure they're not the same. We can tell they're different sizes. And so it makes it really clear right from the beginning that even halves are not equal. And so if I did something like fold a piece into thirds, don't have that one folded yet. Again, I'm going to draw the line so it's very easy to compare. This is clear that one of these is representing a third, and this one is a half, but not exactly clear about, I think maybe even this third of this one is maybe bigger than a half of this one if you try to compare what's going on. And so get the idea that you can't even do simple comparisons with fractions unless we know from the very beginning and we're very explicit about it that we're talking about the same size whole. So again, just to emphasize, the second big assumption is that we better focus on whole, what the whole is, or kids are going to struggle right from the very beginning with what fractions mean. Okay, and this one's a little bit longer because I want to show some of the varied experiences. So the idea we're arguing here is that varied experiences are valuable, and so we'll look at a bunch of examples. So first example we've already kind of done here, but if you didn't do it while I was modeling this, would you pause the video and fold a sheet of paper into halves? And so go ahead and do that. Pause the video, and then I'll come back and talk about hamburger versus hot dog folds so you can see that there's a difference there. Okay, so you may have taken a sheet of paper and folded it in half and have it look like that. This is the hamburger fold. Kind of looks more like a hamburger than the fold in the other direction, which looks more like a hot dog. But this is still a half too, isn't it? Again, I'm going to put the line down so you can see it easily. And if kids are doing this in class and you're talking about some of their foldings, they're probably going to have to do this so other kids can see it. If you hold it up, sometimes you just can't see the fold. Fold's still there. It's kind of hard to see it. Do this. But see, the point here is that those really are both halves. And they actually are exactly the same whole too, but they may look differently. And so you're going to have to deal with that possible, cognitive dissonance with kids when you've got halves that don't look the same. But with little experience, you talk about, well, they're the same wholes. Are they still the two equal pieces that make up the whole? If it was chocolate, would you still have the same amount of chocolate even if I just cut it the different way? Or was it a piece of cake? Would you have the same amount of cake if I cut in a different direction? And I think they will eventually, get that and know that they have choices about hamburger versus hot dog folds. Okay, so now pause the video again and fold that same sheet of paper into thirds. Now what I'm going to do is I'm going to go back to an example that I had with the smaller units, because they may fit down here if I need to show it down on the document camera, or maybe you can see it up here. But take whatever you use as your unit, fold in halves, but take that same sheet of paper and now fold into thirds. So pause the video and do that. So let's just see if it looks any better on the document camera. I may have to zoom out anyway. Again, this will not really be visible until I do the subdivision. So if this was maybe your original half, I don't know if that's really working as well as I want it to. I may just hold it up maybe. Yeah, that's okay. And then if I do, you may have folded thirds like this. So I'm using a different color here to represent the thirds. So you can see it like that. So see both halves and thirds on that same sheet of paper. So that may have been something that you did. You may have generated one like that. On the other hand, you may have, on your original paper, folded into halves, so there's the half subdivision, and then the same sheet of paper folded in thirds and fold it in a different direction so that your subdivisions are, the red ones now in this direction are showing the thirds. Do you see this is a little bit different result for the same problem? Remember, some people may have folded halves and then thirds in the same direction. Some people may have folded halves and then pulled the thirds in the other direction. And I just want you to think about a little bit, which would you prefer? Which one do you think is more powerful, has more potential for doing things? And until you start doing some of the operations, you may not recognize it. But what I want to argue is that this version is really not as powerful as the other version. So I want to encourage you that when you're doing paper folding, or later on when we do some of the area models that you do the fractions involved in the problem. If there are two of them, do them in two different directions. Even use different colors to represent the different directions, because do you notice that on this version right here, I can easily see halves and thirds at the same time, and I can see how they're related to each other. This one takes a whole lot more work to try to see. Even if I wanted to take this and say I want to add a half and a third, how much is that going to end up being? Without doing some more work, I can't answer it here. But on this one, and this is going to be kind of a preview to the area model, if I did a half and a third, half is clearly this much, and a third, I can see because I divided the whole into 3 equal pieces this way, a third is 2 pieces, so if I add that third, those 2 extra pieces on, it's fairly easy to see the result of just doing a very simple computation. A half and a third. So I would encourage this approach of doing the subdivisions in 2 different directions, one vertical and one horizontal. And we just did that. We modeled. We could do a takeaway too if I wanted to take this. Sorry, back on the document camera. I want to take away a third from the half. If that's a half, all I have to start with. A third is 2 pieces. I have to remove those 2 pieces. Not so easy to see what's going to happen if that was what I was starting with the model, with showing halves and thirds at the same time. So operations are fairly easy. And here's just a note. Probably will remember to say this in class. I've sort of trained myself not to do it, but it's a hard habit to break when you've gotten used to writing fractions with a diagonal fraction line. Notice the way that it is on the PowerPoint. Sometimes the word processor you're working with naturally does those diagonal things to represent fraction lines, and in some cases you may have to go to something like math type to get it to do it horizontally, do the numerator and denominator very clearly, over each other with a horizontal fraction line. The problem is with kids is that it's messier, and you can't really tell very clearly what's in the numerator and what's in the denominator without really paying a lot more attention. But when you write it horizontal lines, that's a lot clearer that 2 and the 3 are in the denominator that you see at the bottom there. So try to break that habit. If you ever write it on the board or wherever else you're writing it, to try to force yourself to write with horizontal fraction lines instead of those diagonal ones. The only reason that the diagonal ones were ever used is because of word processing issues, and because people were trying to save space when it takes up less space when you do it. You can get it in a single line, but that may cause some conceptual difficulties for kids. So try to work on that. So again, we're talking about various experiences. So kids need to see paper folding. This is not a new idea. You've heard about multiple representations in your classes and how powerful that is. And so I'm just trying to show you a few different kinds of representations for fractions that are especially important because fractions are so hard. So the more you can take advantage of lots of different representations and activities that the kids are doing is good. And so paper folding is the first one we're going to look at. You ought to do it in your class when you teach. But there are others. So we'll look at, this is kind of a strange one. You wouldn't expect egg cartons to be something that could be useful. But we're going to go back to the first thing, and if you can see that very well, that's what I'm going to call the unit. So this is the whole. And if that's the whole, then this little piece that I put in there, the colors are maybe a little tough to see, but that's yellow and against white. What fraction would that be? So think in your brain, what fraction am I going to call that? And we'll come back and answer that question again. But I think that's a half because it takes 2 of them to make up the whole. So there's a half. What about this fraction? Well, think in your brain the answer. I hope you said, oh, that's clearly 1/3 because it takes 3 of them to make up the whole. And so I can use egg cartons to model all sorts of very simple fractions. We can now also, once I have those fractions modeled, do something really nice, which is to, well, probably the next thing you would do logically is say, well, what was the name of this one? And everybody say a half. Say, well, is there another name? Can I give an equivalent fraction name to this? And, it doesn't take much for kids to say, oh, that's 3 out of the 6 pieces that make up the whole too. So I can call that 3/6. And then this one would have been 1/3, but it's also has the name 2/6. And then I can do even very basic kinds of operations. There's a half, there's a third, and so what do you get when you add them together? Well, we can see that that's taking up 5 of the 6 pieces that make up the whole, and so even without doing common denominator stuff, although it's not hard to do once you think about the equivalent fractions, you know, what's 3/6 and 2/6? That makes 5/6, but I can see the answer is 5/6 very visually here and make a connection to that and what I would do with getting equivalent fractions and getting common denominators. Because it's just like asking what's 3 apples and 2 apples. It's 5 apples. So these are 3/6 and 2/6. Altogether, that's 5/6. So egg cartons can be very powerful, very simple ways of modeling fractions. I probably jumped ahead here. So we can do simple operations, addition and subtraction. You can even do subtraction. So if this is a half of say a whole pound of chocolate, and you have a third of a pound of chocolate looks like this, but if I give it to somebody, I've got to take it from the chocolate that I had. You can actually see a half take away a third of a whole pound, and how much of a pound of chocolate's left? Well, one little piece, but that's a 6. So I can even do, you know, fairly straightforward subtraction operations too. And other units are possible with egg cartons. I mean, you can use you know, a four piece that makes up a unit. You can use the whole egg carton to represent the unit. You can use one that's got 8 in it to represent. So very cheap, you know, and very nice visual kinds of things that you can model some very basic operations and fraction ideas with that manipulative. It's a little bit different than paper folding, and so, you know, it adds to the students' understanding of fractions when they've seen egg cartons. They get into a real problem situation. What they may call up in their head to make sense of that is that egg carton thing that they've experienced. So take advantage of that. Okay, what else we have is pattern blocks is another one. Pattern blocks, we'll get this on the document camera. These are ones that you have kids would have likely seen. Pattern blocks are used probably extensively in early grades because there's a lot of nice patterning and symmetry and lots of stuff for very young kids that you can do with pattern blocks. And so since they're comfortable with them already, then you can do some activities with it related to fractions. So if this is the whole, and by the way, you can let any of them be the whole you want, but let's just let the hexagon be the whole. I'm going to zoom in just a little bit, I think. Yeah. So if that's the whole, then what fraction does that represent? Well, you kind of have to know that it really does take 2 of them to make up that whole, and so if I have 1 of them, then that fraction is 1/2. Kids can play around with this. You can do a lot of fraction tasks with them. What about if the hexagon is 1, if that's the whole, then I wonder what the blue rhombus would be. What fraction would that represent? Well, you kind of have to know how many of them it takes to fill up the whole. And kids will have done this. They're probably already familiar with, you know, the way that subdivides. And so we can model a third fairly easy. You know, and so you can also then, just like with the egg cartons, if that's a half and this is a third, you know what happens when you add a half and a third together. Well, the other part of the hexagon is knowing that it takes 6 of those little green triangles to make up the whole, and so I can see it's a 6 short, so we can argue it's 5/6. I mean, you would want to have the kids generate that by, you know, exploring how many of the green triangles it takes to make up the whole with the hexagon. So it takes 6 of those, so then I know what the green triangle represents if the hexagon is the whole. You know, so you can be creative with that and think of all sorts of different kinds of operations and questions. You can do subtractions. You know, what's a half? Take away a third again. Well, what's left is this little piece right there, which now we already know is 1/6 of the whole. So pattern blocks are nice, mostly because you can model some very simple operations, just like with the egg cartons. But they're also nice because the kids probably are going to be somewhat familiar with those. So I'd take advantage of them because they know about them. Let's see, what else? Some limit to this, just like with the egg cartons. You can't do very many different fraction operations. I mean, you can't do much more than halves and thirds, or maybe fourths or something, depending on what you change with the whole. And so, but that's nice to start. You don't need to start with sevenths and eighths and 15ths and strange things like that with kids when you begin. Start simple, and I think kids will appreciate that. They'll have mental pictures now associated with fraction ideas. They might visualize what they already understand about hexagons and relationship of the rhombus with that. There are also lots of virtual sites out there. If you just do a search for virtual manipulatives, you can find pattern blocks all over the place, and those virtual sites just allow kids to drag those pattern blocks right out there in the play area, and so it's probably in some sense even easier to do it on those virtual sites than it might be to do it with the actual materials. So especially if you don't have materials, know that you've got access to those virtual manipulatives out there that you can also use. All right, so here's a third one, area models. Rectangular area model, we're going to explore this a lot in class because I think they're extremely powerful. They're more powerful than the ones we've already looked at because you can do a lot harder problems. You can do eighths and ninths or sevenths if you wanted to, fairly easy with rectangular area. And all you do with rectangular area is you just have to draw a rectangle. And it's an awful lot like paper folding, except I can easily make the subdivisions with paper folding. If you had to fold sevenths on a rectangle, that's pretty hard to do. But I can make up subdivisions here. And even though they're not exactly precise, I'm going to pretend that they're ideal subdivisions, and so we can call that, since there's 1, 2, 3, 4, 5, 6, 7, we can call this shading right here 1/7. So rectangular models are very easy to generate. Once kids have done it a couple of times, they don't continue to make the mistake that if you said make thirds and they do 3 subdivisions. I mean, typically this is what kids will start with. You do an area model and tell them to make thirds, and they'll make 3 subdivisions, and then recognize, oh wait, when I subdivided 3 times I get 4 pieces. They'll get past that fairly quickly. So I think we'll look at a couple of examples here. So if I want to see thirds and halves at the same time in an area model, so start with what you decide the whole looks like, and I can do halves in this direction. You don't have to do it always vertically. I tend to just, by stubbornness, do it vertically first. And so that's what a half looks like. And again, just like with the paper folding, if you're going to do thirds, then you divide it into thirds the other direction. And I again would strongly encourage you to use colored pencils or something that distinguishes between those, so you can talk about why is it a third, because those red subdivisions divided the whole up into 3 equal pieces. And so that's how I know it's a third. Here's the other thing that you may think kids will struggle with fractions at the beginning, and they will if you don't do it conceptually. Sometimes people will say this part shaded right here is a half because it's 2 pieces, and they're just superficially paying attention to that 2 in the bottom and seeing 2 pieces there. But if it's developed conceptually, which we're going to talk a little bit more about, this 1/2 means the whole is divided into 2 equal pieces, and I've taken one of them, and so the 2 equal pieces that we make up here for this half is this shading, and so there actually are 3 little chunks that make up that half. So if you do it conceptually rather than superficially just counting, kids will get beyond that fairly quickly if you develop it in the right way. But what's nice about this is that, again, just like with paper folding, it's very similar to what happens with the paper folding when we did that one. You can easily do a half plus a third and argue that that's 5/6. So very powerful. You can do rectangles. I don't know if I mentioned thirds and eighths yet, but I'll mention it here, is that I can do thirds And even though they're going to be little skinny things, I can get 8s in this direction. And so even answering questions that involve both thirds and eighths, I can see what thirds look like, I can see what eighths look like, and so I can deal with the whole and understanding what those fractions are and be able to do some operations with it. So rectangular area model is very powerful. I can get some fairly big numbers involved if I want to. Okay, what else do we have? Cuisenaire rods. So Cuisenaire rods, this is going to take a while to get used to. Rods are of the nature that it just takes a while before you start to recognize things. I mean, it'll take a while before you know that the orange rod is a tin rod, and so it makes sense that if I have a tin rod and I know these little red ones will stack across there, they will actually come out to match up. And so when you treat the hole, it's kind of a linear model, that the hole is from here to here, and I've taken that hole and divided into 5 equal pieces, so clearly this is 1/5. And at the same time, you can model halves. This is half of the hole because it takes 2 of them to make up the hole. So notice how I can see halves and fifths at exactly the same time. Cuisenaire rods are really powerful for showing relationships. They're probably as good as the area model. There are certain operations where I prefer the Cuisenaire rod model to the area model, and other operations I prefer the area model to the Cuisenaire rods, but I think both of them are really important. I would never leave that out of instruction if you were teaching kids to do that. And we'll eventually later on do some operations. If I wanted to add a half and a fifth, I mean, that's how much you're going to add. Put them together, so from there to there is what I want to know, and you just go back and measure this with single blocks to see how much that is. So we'll practice that in some of the other videos, but I just wanted you to see kind of a brief introduction to what it would mean to model fractions with Cuisenaire rods and just some very simple operations. If I want to do a subtraction of a half, take away a fifth, then I say from here to there is a half. I've used that much, and so I just measure to see how much is left over. Well, the part that's left over is 3 little pieces, and if you go back to if you went back up here and saw how many of those pieces it takes to make up the whole, you would find it's 10 of those, and so these are 3/10. Again, I'm not meaning to teach that right now. I just wanted to give you a really brief introduction because you will get videos that really develop that in more detail. But Cuisenaire rods is another very powerful model that we can use, and again, as many experiences you can give the kids, the better off they are. We did the thirds and eighths with the area model, but I just want to make the point that I can do thirds and eighths with the Cuisenaire rods, but in order to have thirds and eighths, I've got to go to a unit that's got 24ths, and I don't know if you can, it's not even going to fit on here, but I've got to go all the way, all the way up to a 24 rod to find a unit. This is just going to get a little bit involved if you do some very big numbers with Cuisenaire rods, but so we'll focus on Cuisenaire rods down with numbers that can more easily be modeled and take advantage of that relationship that we see between rods. I do want to mention, though, that they are more flexible. Even though they might be a little bit more cumbersome than the area model, they are more flexible than pattern blocks and egg cartons and circle models that we're going to look at in a second, because those other ones, you don't have, it's not as easy to model a variety of fractions with them. I was intending to see whether or not you could even do this, but I think the video is going to get long enough that I won't do this. But I've got this link in here. If you want, I think it would be valuable for you to pause the video, follow that link. It's one of the best ones that I found on having Cuisenaire rods out available on the web. So again, Cuisenaire rods are not cheap, but you can get access to them through virtual manipulatives, but this one's a hard one to find. So I put this link up here. If you want to stop the video, just follow that link, see if you can get that link recorded in your browser, and notice the kind of things. One of the things that are important, one of the things you're going to find on there is that one has some options for you for what you would let the unit be. You can go all the way up to 12 or 15 or 20 in your unit for the rod, and Cuisenaire rods typically only has a single block, the 10, as far as you go with physical Cuisenaire rods. Okay, what else do we have? Well, circle models. Circle models are very popular. You're gonna see a lot of circle models out there. They're even available. Lots of manipulatives. This is actually one that you can use as overhead manipulatives, and so you can model fractions. You can see all those will fit in there to make the unit. So you can do a lot of modeling of fractions with circle models. I mentioned in the very last bullet there that there are some people that have spent a lot of time looking at fractions with circle models. But I'm a little bit worried about this, so I want to make a point about circle models that maybe wasn't clear, given that the amount of circle models that you've seen in your instruction when you were a child and learning about fractions, probably people use circle models. So what I want you to do is pause the video, draw some circles, and then shade some various fractions. Just make up fractions, see if you can find halves and thirds, fourths, fifths, whatever. See if you can make some different fractions, and then think about which one of those subdivisions in circles were easier to deal with. So again, pause the video, make lots of different examples, and be prepared to talk about which of those were more cumbersome than others. So if we, assuming you've done that, let me just try a couple of things here. Let me see, do the next one here. So lots of times people can do halves very easily. So here's a circle with a half in it. And you could do a circle that has thirds. And all you have to be able to do is get close to drawing something that looks like the peace symbol. Those are thirds because they make them up. But the issue that I want you to think about is, that's a little bit harder. And what if you had to do fifths? That's even maybe harder for kids to be able to do. Fairly easy to do halves and fourths and eighths, because you can just take this half and keep subdividing in other directions. If that's half, then this is fourths, and you divide each of those in halves, and you're going to get eighths. So I can do halves and fourths and eighths fairly easily, and probably add halves and fourths and eighths. But that's kind of restrictive, and here's the point I want to try to make. Here's the third that's modeled. But if I model a half at the same time, and I don't even really know where to put it, I could put it across this way, and it'd be really confusing. Halves and thirds at the same time are really hard to do. Even if I'd done the subdivision down this way, it wouldn't be much more helpful. So the problem with circle models is they're in some sense one-dimensional. You're drawing just out from the radius. All your subdivisions are always out from a radius, and that's different than when you do paper folding or area model, where you can do two different dimensions. Some of your subdivisions are horizontal, some are vertical. This one, I think, has just a lot more potential to be able to model problems. I think circle models are a problem because you can't even do halves and thirds very easily in a conceptual way. I mean, there are ways around it that you can do a half and a third, but to me it's a little bit contrived. I guess I ought to, though. Well, let me just make this point first. So I think there are limits to this. You're stuck with halves, thirds, and fourths. So be careful with instruction in fractions that focus on circle models. And you may actually even find that your textbook will have a big focus on circle models. And as a reflective decision maker in the classroom, I'm hoping that we'll get you to the point where you say, that's not going to be sufficient to just have the kids do circle models, especially given the one-dimensional nature of it, and that it's difficult to even take the simplest set of fractions like half and a third and be able to see what you get when you add them together. But in fairness, I'll mention that some researchers really have spent a lot of time. Maybe they started with a bias that circle models are important, but they spent a lot of time exploring circle models and are more comfortable with encouraging their use. And if you want to see some of the things that have been done, you can actually do a search for Rational Number Project. It's an NSF-funded project that's been in place for a long time. They really focus a lot on circle models, and they do a lot of things that are related to this manipulative that I showed you earlier. It's just that in order to do operations, you got to generate all these little pieces in there first, and you got to already know, the color that looks that 1/8 looks like, or 1/10 looks like. It to me is a lot more cumbersome than just doing an area model thing where you already know that if you want halves and thirds, it's very easy to generate that by drawing in different directions. So I don't know that there's a consistent view on what's going on with circle models, but I would at a minimum encourage you to be careful with it, because a lot of textbooks have never really thought through that issue, and they still have a lot of circle models used in their introduction to fractions. Okay, there are other models, and I'm not going to share any more of those here, but you will see in a couple of videos that are included on the online activities section of Blackboard. There's a video that's entitled Positive Rational Numbers, and that one I think explores number line models of fractions. So having the kids be engaged in trying to see where fractions are on a number line is another one of those representations that's probably extremely important. And so you'll look at some activities there that I think will help you think about what you want to do with kids. And then the second one is just called fraction strips, and they explore using fraction strips to model fractions and some fraction operations. So there are others out there that I think you ought to look at. And in fact, at least for my class, these two videos will be assigned. By the way, this is probably the two videos that you should do immediately after this one. This is kind of an introduction to the idea. These are some other basic ideas. You should probably look at this video immediately. I mean, there'll be a lot of others you're going to be engaged in, but this is probably the first one you should look at, which is the next bullet. Okay. All right. So that was all of the talking about various representations of fractions. I hope you already understand how important that is, that you just don't give kids one model. If all they can ever think of is circles when they're given fraction problems, then that's probably a very limited understanding. They're not going to be as powerful if all they can visualize is circle representations of fractions. So the fourth big assumptions that we want to make about working with fractions is that powerful and extensive early experiences are essential. If you want later understanding of fractions and fraction operations, you are going to have to work really hard early on. You can't just jump into operations and expect that magic happens and kids will develop concepts because they've been doing operations. I mean, the worst example of that is what we tend to do now, was where you just train the kids about how to get common denominators and do paper and pencil computations with fractions, and either don't care that they really understand what's going on, or we just make the assumption that all of a sudden magic's going to happen and they will understand what those fractions mean. And I don't think there's much evidence of that. So I just got a couple of slides here that talk about some of those early ideas that you better make sure you focus on. And the first one listed here was just fraction concepts, and that just means doing a lot of naming of fractions and modeling of fractions, having the kids actually model fractions with various materials, just like what we've been doing with all the Cuisenaire rods and area model and paper folding and all the models that we just looked at. Have the kids be engaged for a long time in making and naming when you make it or when somebody else makes it, that they can recognize what 1/3 looks like. And the point is that these multiple representations actually provide meaning for the fractions. It's not just how you write 1/4 on a paper that's what a fraction is. And that's the problem I think that a lot of kids struggle with fractions now, is that if you say 1/4, the only meaning they have is that they've been trained to write 1/4. And all they've got is that paper representation of it. They don't have any conceptual basis for what's going on. And so all of these multiple representations that we have with using various materials is extremely important to give meaning to those numbers, because the numbers have to have meaning if the operations, when you start adding or subtracting them, are going to make sense. So do all that early work. Don't skip over it, or your kids will be having trouble. So the first one is modeling, naming in various contexts, various materials. Second one is the idea that just like other numbers, you need to develop the meaning for fractions as a concept in action. And I'll give you a couple examples of this. So it's really like saying, well, what is the meaning of 1/4? What does 1/4 really mean? And I make the argument that fractions are concepts just like any other number. If you consider the number 3, when we have 3 objects set up, yes, you want a child to recognize that that's 3, that there's a 3-ness associated with this. But what it really is that there really is a concept in action associated with this. And I'll try to get my finger in here so you can see what's going on. That the child, when they see this, they know this is 3 because they are taking an action where they've kind of separated out this object, you know, from the rest of the thing. It's like they put parentheses around and say, oh, there's 1, and they make a connection and say with a number word and point to it and say 1, 2, 3. So there's actually an action involved in the concept of 3 or 3-ness. And so don't think that I'm asking you to do anything different with fractions than you would with any other number. So what is this concept in action related to fractions? Well, first I'll make a point of this. The question is, should all concepts be concepts in action? And there's a mathematician named Percy Bridgman who made the argument that it should, that all concepts should be concepts in action. And that action needs to be completed before you start talking about what it really means. I'll make an argument here that it's not just in math, it's in lots of other things, even something as strange as the concept of love. And so I apologize for this story, but it's here to make a point, I think, is that even the concept of love. If I ask you what love is, what would you say? Well, I got a rude awakening into that question when I was planning to get married. The preacher who was going to marry us said, you know, well, my requirement is that you come in for counseling. I don't do marriages without counseling. And so he gave us some books to read, and then we came into a session one day, and he said, why do you want to marry her? And I said, fumbled around a little bit and said, well, because I love her. And of course I just set him up, because the first thing he said was, what does that mean? And so then I really fumbled around, and we may mention this in class, but and I know this is an overgeneralization, but one of the things I discovered that day is that, sorry if there are any guys in the class or any guys listening to this video, but honestly I think women understand that better than men do. At least in this case, my wife understood it. She had a much better answer than I did, because her answer was, love is an action. You know, love is not an emotion. Love is the actions that you take, to demonstrate, how much you care about somebody else. It isn't just an emotion or words or rhetoric that you say. And I sometimes even apologize for this, but I think it's a good example. I even give an example from religion. That there's a quote in the Bible that says, if you love me, then you'll keep my commandments. So it isn't, if you love me, you have all these nice feelings, but you do what I ask you to do. That's how I know that you really love me. So I'm just trying to make the point that love even is, I think, a concept in action. So I don't know why our number concepts ought to be any different. So here's what I want you to think about. Pause the video and try to write your best guess about what 1/4 might mean as a concept in action. So take just a little time, pause it, actually write something down. What does 1/4 mean as a concept in action? Okay, so I'll give you what I think might be an example of what it means as a concept in action. I've probably already said it when I modeled it with some of the other materials here, but I think you could argue that 1/4 means do this action. First, consider the whole. Pay attention to what the whole is. That's an action involved. And then you take the whole and you divide it into 4 equal pieces in some way, either mentally or with paper and pencil or whatever, or folding or whatever you're doing. And then you pay attention you focus on one of those pieces. That's what 1/4 means. So you're focusing on it, either say I'm eating 1/4 of a pound of chocolate, or I'm going to take away a fourth of a cup of sugar, or I'm going to give away a fourth of an ounce of gold or something. So you focus on that one little piece once you divide the whole up into 4 equal pieces. So, and I think that's extremely important, that kids all have some kind of concept in action, so that when they see the number 1/4, they know this is what I do to make sense of that. Also, something that's very essential very early on, and we did a little bit of this earlier when we modeled it, because it's hard to avoid doing it at the same time you're modeling this. But you know, if you name, let's go back to the, if you name this subdivision here with the green subdivision as 1/2, you also have another name for it. It's very clear that's also 3 out of the 6 pieces that make up the whole. So we've been doing that all along very naturally. When I use nice models like this, equivalent fractions will flow naturally out of what's going on. But it turns out that you can't do much more. Even very simple operations here require that a student kind of get an idea of equivalent fractions, that this is 3/6. The third here is also 2/6. And so when I add them together, it makes sense that it's 5/6. So do not leave out work with equivalent fractions. I mean, yeah, with all sorts of materials. Got to have kids being very comfortable with that. The operations won't make a lot of sense. And students should be comfortable generating equivalent fractions in a variety of contexts, but I would say especially area model and Cuisenaire rods, because those are very powerful. So make sure they've had plenty of work doing that before you start introducing them to operations with Cuisenaire rods and area models, because those are sometimes a little bit complex. We will actually see later on, so you know how important it is, that many of the paper and pencil algorithms that develop out of this work really substantially use these equivalent fractions. So it's going to be really important work to do. Okay, got it. I think last one here on early kinds of things to do is this writing fraction situation. So the idea is that the language involved in stating a situation that fits one of these operations. In other words, if I'm trying to distinguish between subtraction and multiplication, it turns out that that language is very difficult, and you have to be extremely precise with the language. And so kids need a lot of practice actually writing fraction word problems and focusing in on the structure of those word problems and what actually makes them subtraction, what makes it multiplication. I'm sure we'll do a lot of work on this in class. It's mentioned in this first bullet here that there's a fractions word problems lab. It takes some of the problems that I'm about to show you, some of the examples here, and ask you to say, well, what is an error here? And so the purpose is that you identify typical errors in other people's work so that you're more likely to recognize when you're writing your own problems, oh, that's something I better watch for because I don't want to make that error. So we'll just look at a couple of examples here. And there are lots of different kinds of errors that you can see, so I probably won't get to all of them on here. Oh, too far. So just look at number 1 here. It says that a dog show there were 2 2/3 poodles and 1 1/2 Dalmatians. How many dogs were at the show? Well, the structure is okay, but what you might notice is, well, that's kind of a strange context. I mean, how do you really get 2 2/3 poodles, 1 1/2 Dalmatians? People argued that maybe it was a veterinary show and they were doing surgeries or something. I don't know, but typically what you want to do is make sure that you're trying to write word problems that are meaningful, that are not, they're not really strange, you know, that they ought to fit a real kind of situation. So make sure they're reasonable when you write them. Let's look at number 2 while we're here close. I have 1 2/3 cup of milk. I want to make a cake that calls for 2/4 of a cup of milk. How much of the 1 2/3 cup will I have to use? Well, you know, again, the structure is not too bad there, and I'm not really sure what operation it is, but because I don't know how to interpret this, how much of the 1 2/3 cup. Is it asking what fraction of the 1 2/3 cup of milk I need to use? But in that case, I would argue that's not something you'd ever want to know. So probably what this person was asking is, how much milk do I need to use? But I'm using it from the 1 2/3 is what they were trying to say. But the way it's stated here, the recipe calls for 2/4 of a cup of milk. I don't know probably should have said a half there, but that's okay. But what's the point? How much milk do you use? Well, it's given to you in the problem. You're using a half a cup of milk. So be careful about not writing questions that already have the answer in them, or that you write in a way that you're not really sure exactly what's being asked there. I'll show you number 4, although I don't really know what to say about it, because I've never, ever really been able to figure it out. Charles owns 1 1/3 stores full of books. If he sells 2/5 of the whole store, 2 stores full, how much of the store does he still own? I mean, I just don't even know how to interpret that. So be careful about making things clear and ask exactly what it is you want to know. I'll just do a couple more here. Let's do number 5 since we're on this page. My yard covers 4/8 of an acre by 5/8 of an acre. What's the area of my yard? Actually, the structure of this is pretty good. If you're thinking of giving a length and a width for a rectangle, you would typically multiply to find the area of what's going on there. So the person is wanting you to multiply 4/8 times 5/8. And this one takes a while to figure out what might be wrong with it. Think about it a little bit. See if you can figure out what's happening on this one that's a little bit goofy. This one is just one that somebody has used the wrong units, because 4/8 of an acre. Acre is already a unit of area, and so it's not really describing the length and the width of this rectangular yard. It's using a unit of area already, which is not what you use to describe length. So something is goofy with that example. Okay, let's look at number 6 here. Eugene walked 1/4 of a trail. How many more kilometers does he have to walk? When you think about that for a while, it gets fairly obvious. Well, it doesn't have enough information in it to solve that one. And then my all-time favorite problem, just because it's funny. And by the way, we're doing this. These problems actually came from a class just like you're sitting in right now, or the class that you're enrolled in. This mathematics for elementary teachers. These people in the class actually wrote these problems, and I just compiled them and put them together. And the intent here is not to make fun of them, even though we're going to laugh at some of them. This one I think is funny. But it's not to make fun of the people because they didn't know any better. It's not their fault. They hadn't had a chance to practice writing fraction problems before, and so it's very natural they would write some with errors. But what we did was decide to use those initial problems that had errors in them to give us something to talk about so that you would know to watch for that and not make them yourself. So we're not really intending to make fun of people on this. We're using it as a learning experience. But I really like this. Billy Bob had 1/3 of his tractor working. He fixed a half more of his tractor. How much is now working? So if you think about that one, I don't know how you even measure that 1/3 of a tractor is working. My perspective, a tractor either works or it doesn't. And then I don't know what's a half more. I mean, is the power take off a half? I don't know how you figure that out. But anyway, funny problems, but be careful with stuff like that you try to put units on things that you can't really figure out what a half of a tractor is. One more. Number 12. Adam had half of a cake. He gave Dexter 1/4. How much did Adam have left? So what's the problem with that one? Think about it a little bit and see if you're remodeling that, what would it look like? So what we'll end up eventually watching for is making sure we don't ask ambiguous questions. Even if you said he gave Dexter 1/4 of it, what I strongly encourage is never use pronouns because you can't tell what the it refers to. But in this case, 1/4, we don't know what 1/4 is. Is it 1/4 of the whole cake, or is it 1/4 of what Adam had? And it makes all the difference in the world depending on whether that's a subtraction or a multiplication. Even though it says how much is left, we'll apply subtraction. But you may have to do a multiplication first if we don't know what this 1/4 refers to. If it's 1/4 of a whole versus 1/4 of what was there, it makes a big difference. So you got to work hard on fraction questions. And so I think that's a valuable thing to ask kids to do. It's also valuable, I think, because it gives you a good assessment tool for the teacher. If you ask Johnny to write a subtraction of fractions word problem, you can get a pretty good idea of whether Johnny is really getting the idea of the structure of a word problem or a situation that makes it subtraction. It's a good assessment tool. So having kids write fraction question situations, I think is really important. And that's why I'll emphasize it in our class. You're going to write a lot of questions. You'll do it on tests. You'll write your own questions because I want to know, do you understand the structure of that? Okay, last one. Last big assumption you want to make is that usually what happens is you do some fractions for a while. If you do it in the right way, which we'll see here in a second, is that you start with some concrete kinds of things and you model that and you build up the ideas. And then at the end, it's very natural to move to an abstraction where you're starting to write paper and pencil computations to represent fraction operations. But I want to make the argument that any paper and pencil algorithm is meaningless unless it's developed from operations with materials. And the argument I want to make is depending on this idea of, do you remember Piaget and how much you've studied Piaget? And the discussion is that student activity should move from a concrete to a semi-concrete to semi-abstract and then an abstract. So you start with very concrete kinds of things, so you build up what the meaning is of the ideas, and then you gradually move to more powerful, more abstract ways of operating in that, so that you don't always have to pull out materials when you're ready to make sense of something. But the point that people miss is they focus more on that we want to get to the abstraction because it's more powerful, and then they skip all those intermediate experiences that are important to get to the abstraction so that it makes sense. So we do a lot of instruction with kids in schools where we just tell them to practice paper and pencil computations, and they never really know what's going on or where that would have come from if they just started at a concrete level. So this ought to happen with fractions too. That abstraction needs to be able to be unpacked so you can see where it came from. There needs to be a link between the abstraction that you want the kids to get to and the concrete things that they did at the beginning. I mean, people have understood that for a long time. Piaget talked about it. It's a part of your courses on teaching and learning. That they make a big deal about how Piaget had good ideas about that, and then we turn around and have a curriculum that just starts kids working up here at the abstract level, making them do paper and pencil stuff, and again, then we kind of expect some miracles going to happen that they'll really understand what is happening. So you need to have that link. And so if that's the case, I want to make the point that that abstraction is really only a record of the concepts and operations that you already know how to do, that you've already sorted out, that you've made sense of, so that when you say I'm going to be a little bit more efficient in it, those things that you write down is not the real math. The real math happened here. It's only a record of the real math and the real understandings, the real relationships that you've already established. And that needs to be done down at the concrete level. So you have to build this up in the right way. And I'll go back and make the point again, that takes a while. So if you really want this done well so that kids get fractions, it's going to take a while to get through all the concrete and the semi-concrete until we get up to those abstractions. But I think it's healthy for you as a teacher to remember the abstraction is not the ultimate goal that I have. It's just a more efficient way of keeping a record of what I understand. It's the understanding that I think is what you're ultimately after with the kids. That's just a kind of a side thing that allows me to be a little bit more efficient with some abstraction. Just a record is all it is. Nothing special about it. So here's what's going to happen with fractions. If we really want that connection, that link to be made, we may have to consider some alternative algorithms, because if the traditional ones don't naturally grow out of that work at the concrete level, then I don't think we should be using them. We're building concepts at the concrete level. If you think about it, there is no multiplying straight across that you do with area models or with Cuisenaire rods or with paper folding. I don't know what that would mean to multiply straight across. And there's no inverting, but we didn't turn stuff up and multiply whatever it would mean to multiply Cuisenaire rods. You just don't do that. So there is not a link for those standard paper and pencil operations to the way it was developed. But it does turn out there's a really nice paper and pencil abstraction that is linked to what you did at those earlier concrete levels. And so we're going to learn a couple of new algorithms that actually is showing up in a lot of the curriculum now, because curriculum writers have discovered that it's important to use algorithms that link to what you would do at a concrete level. So we will really de-emphasize that multiply straight across and invert and multiply kind of algorithms that are going on, because it's a mismatch. So that's the end of it. I hope you kind of get some ideas on fraction operations. It may be a long video. I hope that you had a chance to think about doing some things, but But here's the assessment I want you to do to bring to class, to actually just go back and list those 5 assumptions that we made. And then to get some reflection on this, I want you to think about some key point, something that was especially meaningful or something you say, oh, I never heard that before, and that's really interesting. Write down something that was a key point from your perspective about each of those 5 assumptions. Just bring that to class, worth 5 points since there's 5 things. Okay, good luck with fractions.